A warm welcome. This is Control Systems course with lecture 3.5 focusing on correlation between time domain and frequency domain specifications. Let us see about the correlation between the time and frequency domain specifications. For that, let us consider a second order system. Standard transfer function is C of S by R of S is equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. Now, in order to introduce the frequency term, we get, let us put S is equal to j omega. And we have the terms. Let us cancel out the numerator part. For that, what you are going to do is you are going to divide the numerator as well as the denominator by omega n square. And now let us take the normalized frequency value u equal to omega divided by omega n, where omega is a frequency and angular frequency and omega n is the natural frequency. By introducing the term u, the transfer function becomes 1 divided by 1 minus u square plus 2 zeta ju. So the denominator term is a complex term. Now let us take the magnitude and angle of this transfer function. We have the magnitude term to be the denominator term becomes root of 1 minus u square the whole square plus 2 zeta u the whole square. And the theta value, the angle value is nothing but minus tan inverse of 2 zeta u divided by 1 minus u square. The 2 zeta u term is the imaginary part and 1 minus u square is the real part. And the angle is a negative angle because the transfer function value is present in the complex term is present in the denominator. And now we know the frequency domain specification values like resonant peak, resonant frequency and bandwidth and phase margin are given here. So the MR value, that is the resonant peak value, is given as 1 by 2 zeta into root of 1 minus zeta square, and omega r is equal to omega n into root of 1 minus 2 zeta square. So now what we are going to do is, in order to find the correlation between the time and frequency domain specifications, we are going to consider two different values for zeta, right? First term, let us put zeta is equal to 0. Second term, square root of 1 minus 2 zeta square is taken as 0. So let us see, in this condition, when zeta is equal to 0, what happens to the MR value? Obviously, it is infinity. And while seeing about omega r value, it is equal to omega n when zeta is equal to 0. If suppose root of 1 minus 2 zeta square or 1 minus 2 zeta square itself is 0, we can see the MR value is indeterminate. You can't determine the value of MR since omega r is equal to 0. Omega r is equal to omega n into 0. So obviously omega r is 0. Since omega r is 0, it is directly reflecting that there is no resonant peak value. This is what we are going to express in terms of graphic. So graphically, we can see that in the first case, while seeing the left side figure, we can see when zeta is less than 0.707, we have MR value to be an infinite value. It is of greater value. But when the zeta becomes greater than 0.707, there is no MR value, and obviously the value of magnitude is getting decreased. So when m is equal to 1 by root 2, we can see it is a cutoff frequency. And when m is greater than or equal to 1 by root 2, it represents the bandwidth value. So what we can infer from this is when omega b is equal to omega c, that is when the bandwidth is a measure of, since bandwidth is a measure of transient response, let us consider omega b is equal to omega c, and at that condition we come to conclusion that the ub, that is the normalized frequency, becomes omega b divided by omega n. And here, while you are looking at the phase angle value, you can see that when the zeta value is equal to 0.707, at that point we can see I mean when u value is equal to 1, that is omega r and omega n is equal, or omega b, yes, it is omega and omega n are equal. At that point, the u value will be equal to 1. That is, the normalized frequency is equal to 1. And at that time, the angle alpha is equal to minus 90 degrees. Now we can clearly watch this. Now, so while looking at the normalized bandwidth, as theta increases and theta reaches 0.707, the UB value, that is the bandwidth value, maintains to be at 1 while drawing UB value with respect to theta. And now coming with the value of zeta to be 0.707, we can see that the resonant peak value is getting decreased from an infinite value and it will stop there. After that, there is no MR value because we can't say the MR value after that, since there is no omega R value. And you can see the MP value. The MP is nothing but the maximum peak overshoot. That is, it is the time domain specification whose value is nothing but e power minus zeta pi divided by root of 1 minus zeta square. We already have discussed this about in earlier videos. And this MP, we can see as zeta increases from 0, MP value is also getting exponentially decreased from value 1 to 0 and reaches the value of 0 when zeta is equal to 0.707. So we can see as a function of zeta, both MP as well as MR are reflecting their values, or they are representing their values. There is change in MP and MR value when a single theta term is changed. Similarly, we can see that the omega r divided by omega d. Omega r is the resonant frequency and omega d is the damped frequency, where omega r is nothing but the frequency domain specification and omega d is the time domain value. So that ratio between omega r and omega d will be varying with respect to the zeta value. As zeta value is equal to 0, the ratio is equal to 1, and as zeta value increases from 0 to 0.707, obviously the omega r by omega d value becomes 0. This is how we can say the time and frequency domain specifications are correlated. Thank you.